Let's talk about the next level of problem, which is putting R, L, and C together in series. There are other combinations, and there are combinations involving batteries we're not going to get into in this course. The simplest example is to put all three of them in series, start with a fully charged up cap, and let it go. The mechanical analogy of this is quite interesting. It's just the mass, which would be the inductance, the spring, which would be the capacitance, and now you have to put a resistance. The resistance cannot be friction, so I took care to make it smooth. The resistance has to be velocity dependent. In other words, you need to have something like an air drag or viscosity. Air drag, I have indicated here by a blowing fan, is controlled by the parameter B. Now on the electrical side, we actually know more than we do on the mechanical side because air drag is usually not taught as a subject in UP1. So let me look at the electrical side first. The kinetic energy, as it were, is actually the magnetic energy of the circuit, and that's given by 1/2 Li squared. Let's write its analogy here. The kinetic energy is 1/2 mv squared, where the inductance L is just the same as the mass m. So I'll put a list here of all the analogies. X, which is position, is the same as charge. Velocity, which is the rate of change of position, is the same as rate of change of charge, known as current. And these are all lowercase because they change with time. And the mass is linear inertia, same as electrical inertia. Now, on the electrical front, the capacitor is going to store a charge, so we know how to write that already. It's 1/CQ squared. From the previous video, we realized that was the most appropriate formula to use. For the block spring fan system, the potential energy is that of the spring. So here we'll expand our analogy list. K is the same as 1/C. That's a surprising thing. Most people think K is the same as C. Well, it's like C, but the exact correspondence is 1/C. The power dissipated is well known to us from circuit theory. It's I squared R. How would we find something like the frictional power dissipated? This is something you don't know. Again, by analogy, you look at the left side and deduce what the right side should be like. Frictional power. Well, current is velocity, so you put V squared. R, well, the bigger the drag coefficient, the bigger the resistance to motion, so the drag coefficient is exactly like the resistance, so I'll put B there, which gives us our final item in the correspondence, and that is the drag coefficient is the same as R. Now, by the way, there are two kinds of frictional drag coefficients for those who are interested in complications. Actually, there are several kinds, but two main kinds. At slow speeds, you use the drag coefficient that's called B, and that's proportional to velocity. That's what I'm interested in, because Ohm's law is a proportional to velocity kind of thing. V equals IR. And then, for FYI, forces are the same as voltages, believe it or not. So if you write F equals B times V with a negative sign, that gives you the drag force. Well, that's similar to V equals I times R by Ohm's law. So at high speeds, like race car, or these are the high speeds that you cannot attain with your ordinary vehicles, but in car racing, for example, when they have spoilers and things like that to keep the car down at high speeds, there you have to use the drag coefficient C, where the drag is proportional to speed squared. And if you're going really fast, like in supersonic aircraft, you have to use a drag coefficient D, where it goes as velocity cubed, and so on. We're not going to get into any of that. So let's try, because the mechanical side was not at all done in UP1, and I know this because I teach it, let me write the mechanical side of things. Newton's second law says the sum of all the forces equals mass times acceleration. What are all the external forces here? Well, there's one coming from the spring and there's another coming from the air. So spring's force is negative kx by Hooke's law, and the drag coefficient times v is the drag force, and that's equal to ma. That looks pretty good. Neat equation. So I get ma plus bv plus kx equals 0. So I'll choose to work with this, and then at the appropriate time I'll shift over to this side and do the analogies. Okay, so let's do that. So this gives me m d2 x over dt squared plus b times dx over dt plus k times x equals 0. This is what's called a second order linear ordinary differential equation, or LODE. Now, how are these loads solved? If you look at the previous video, I show you a technique known as Euler's ansatz. Our man Euler saves us again. Euler's ansatz will be tried once more, and that is e to the lambda t equals x. So when you put this into your expression, what happens? I'm going to get m times lambda squared, because I differentiate twice, e to the lambda t, plus b times lambda e to the lambda t plus k times e to the lambda t equals 0. Now e to the lambda t is common to all terms, and that cannot be 0, otherwise we'll have the so-called trivial solution. So the only possibility is m lambda squared plus b lambda plus k equals 0. For you mathematics aficionados out there, this is called a characteristic equation. And I'm sure it answers to most of your instincts, because I read somewhere a t-shirt that says an engineer is nothing more than an applied mathematician, and as we all know, t-shirts are always right. So this is our equation. How do you solve this? Well, this is our good old friend, the quadratic equation, nothing to get worried about. So lambda equals negative b, the middle coefficient is even called b for our convenience, plus or minus square root of b squared minus 4mk divided by 2 times a, which is 2 times m in this case. And that's it. Once you have these two solutions, which I'll call lambda 1 for the plus, actually let me call this lambda plus and lambda minus, plus sign and the minus sign. Once you have those two solutions, you can write down the full solution, which is x equals e to the a times e to the lambda plus t plus b times e to the lambda minus t, and you're all good to go. The only subtlety in this whole thing comes from the square root sign. You can have three possibilities, and the three possibilities are b squared minus 4mk is bigger than 0. That turns out to be a very boring thing, because if it's bigger than 0, this quantity is bigger than 0, and then you're going to get a combination of a growing exponential and an exponential that's, a decaying exponential and an exponential that's also decaying. And the reason for this is b squared minus 4mk is always going to be less than b squared. So when you take a negative b and add it to something like square root of b squared minus 4mk, you'll still get a negative quantity. So it's going to be a combination of two decaying things, and that's called a overdamped case. Overdamped, by the way, is not a bad thing. It's what you need. For example, if you have a good car and a good suspension in a car, high quality car, it won't bounce much when you hit a pothole. These parameters have been carefully adjusted so that the moment you hit a pothole, it just doesn't even bounce. It just feels like you've ridden over a small rock or something. That would be the overdamped case. So a good car suspension should be designed like that. If b squared minus 4mk is exactly equal to 0, that's called the critically damped case, because that's when, let me put these names here, overdamped. And the critically damped case is just an exponential with a slight growing potential, but exponential will still kill it. So it's slightly bigger than that. This one is a little bit tricky because if b squared minus 4mk is 0, you only have one root. Then you have to use the second Euler ansatz, where you have to, or the Euler polynomial ansatz, and get the second solution by assuming the second solution to be a polynomial version of the thing. I won't get into that. That's something for the differential equation class in mathematics to handle. So that's a critically damped case. And the last case is the most interesting, and that's the underdamped case. B squared minus 4mk is less than 0. If it's less than 0, then you're going to get complex numbers, because square root of something that's less than 0 means you have two complex numbers staring at you. So what we can do instead is to define a constant b prime squared, which is going to be the square root, which is going to be b squared minus 4mk, and write everything in terms of that. So if I take the square root of something that's less than 0, which means it means that, let me actually define, well, actually no, this is correct. So I'll get plus or minus ib. So when I take the square root of this, because this is less than 0, I'll get plus or minus ib prime. So I think I was right in putting the negative sign there. If I put a negative sign there, then that's guaranteed to always be real. So I'll get these two as the solutions, and then I'll get lambda plus as negative b plus ib prime over 2m, and then lambda minus as negative b minus ib prime over 2m. The most interesting thing is those two solutions will have a decaying exponential part and then an oscillatory part. So now I'll, without any further ado, transfer all our learnings from here directly to the RLC case. So I'm just going to plagiarize everything I learned here. So here lambda is, the characteristic lambda is going to be negative b, which is negative r, plus or minus the square root of r squared, minus 4 times mass, which is inductance, times k, which is 1 over c, divided by 2 times the inductance. Okay, that's your lambda. And the most interesting case is what I'm going to be looking at, and that's the underdamped case. So let me just focus on that. So what I'm going to do here is write down my definition of b prime. Now, because b is r, I'll call it r prime. The reduced resistance is r squared minus 4L over C. All right, so once you have that, we can write our solutions in exactly this form. So I'll write this as Q of t, because x is the same as Q. Q of t is going to be A times lambda plus is going to be r plus r prime and so on. So I'll write all that here. E to the minus r over 2L, and then e to the plus I r prime over 2LT, that's also multiplied by t, by the way, plus b times e to the minus r over 2LT minus I r prime over 2LT. That's our full solution. It looks kind of weird, so what I'll do is I'll take e to the minus r over 2L times t outside as a common exponentially decaying factor, and then here I'll make the executive choice to write it in terms of cosine and a phase. Okay, so I'll write this as C tilde. If you look at the previous video, that was my notation when I do this. Cosine, now this r prime over 2L times t plus some phase factor phi. This phase factor is very important in electrical circuits, and there's an entire theory known as electrical phasor theory developed using just the phase constant. So if you're electrical engineers, you'll be spending the rest of your life doing phase diagrams based on this. So this gives us the complete solution. let's write the graph for this. Q as a function of time. Starts out at time 0, like that. I'll first draw this envelope. This exponential part is called the decaying envelope. And then the decaying envelope is going to control how much of the cosine oscillation I see. So I don't know how it's going to start because of the phase factor phi being unknown, so I'll just start it somewhere. What I should have done to make this graph drawing a little bit easier is to have drawn 2 of these decaying envelopes and then sandwich the graph in between. But you get the idea. It's a decaying exponential that's oscillatory within. So if you have a system that's underdamped, then it'll behave just like what you expect a simple harmonic oscillator to do in the presence of air drag. It'll oscillate less and less and less and less. It'll never stop oscillating according to this mathematical thing, but in reality you know that that's never going to happen.